Okay, so thank you very much for the invitation. It's really an honor to be here. Can you hear me well in the last row? I'll try to speak as loud as I can. So I hope this works. Okay, I'll speak about symmetry mostly and a little bit about similarity. And let me start with a quote from a book by the mathematician Hermann Weyl from 1952. Well, I think we all have an idea what symmetry is, and it's used often just to express some sense of harmony of proportions. It's not always clear what it means. We'll see later what it will mean in this talk, but let's just see a few nice pictures about symmetry. So symmetry was certainly there long before humans were there in nature. Well, the butterfly is an obvious example of something symmetric, but also if you see, for example, these flowers have some nice symmetries. And here's another nice one from nature, that's a spiral cactus. We also have symmetry in the arts. That's a ceiling of a mosque in Isfahan. If you look at the ceiling here, you find a lot of symmetry. If I had known I would speak in such a room, I probably would have looked for pictures from that. So symmetry has been in the arts for a long time. It has been in nature. Our kids learn about this actually even in elementary school. And let's just see what kind of symmetry we have there. That's another nice example. It's a very old vase from Sumerian times, couple of thousand years old. And there you have a very nice symmetric picture on it. So here you can see it a bit better. And that would be an example of what the kids learn first, at least my kids. They would put a mirror in the middle, and then you have this nice symmetry. And I'm sure you all know about this. We have other forms of symmetry that we would also learn about at school. Something like rotational symmetry is probably the next best known example. So if you look at this one, that's actually quite interesting. In a sense, it's very similar to the previous picture, except that if you look at the arms, they are somehow flipped over. So the symmetry we observe here, you couldn't just put a mirror in the middle, but you would have to rotate this figure to the other side to get the right arm position. So that would rather be a rotational symmetry. And what you can see from this, that people were well aware of these issues a long time ago. Okay, so now let me move on to symmetry in mathematics and closer to the topic. So what does symmetry mean in mathematics? It's probably something like invariance under a set of operations. Now that is very abstract, but now let's just look at some examples of such operations. So we have reflections that would exactly correspond to mirror symmetry. You just flip and you can flip back. We have rotations corresponding to the rotational symmetry. We also have translations as a form of symmetry. And all these are very well-known operations that we can probably imagine. So maybe let's look here at the octahedron. So what kind of symmetries does it observe? Well, we can see, we can reflect, for example, at this plane or at this plane, actually in various positions. I'm not going to go through all of them. So certainly we have a number of reflections that leave this octahedron invariant. We also have rotations, of course. You can see rotation axis, for example, through the top and bottom corner, and we can rotate around this. We don't have translations here. For translations, we would maybe look at a picture like this, continued infinitely on both sides. Then if you shift it, that would be a translation. It stays invariant. It stays the same if you just shift the right distance. Okay? So that's the idea, but then you can also look at other operations. And the nice thing about this is that the symmetries of an object themselves have a nice structure. They have a nice mathematical structure themselves, which is quite interesting. So if we look at all symmetries of one object, like the octahedron on the previous slide, so what can we say? Well, if we compose two symmetries, apply one first and then the other one, the result will still be a symmetry of our object. So symmetries are closed under compositions. And also we can always invert them. We can always rotate back. We can flip back. Now, if we have a mathematical structure with these properties, then this is an example of what we call a group in mathematics. And that's just something to keep in mind, because later we will exploit this structure algorithmically. So we have some object, like the octahedron. We look at all the symmetries it exhibits, and on these symmetries, we have a nice mathematical structure that we hope to exploit later. Now, this group is called the symmetry group of the object, or the automorphism group. And again, that's something we'll see later. Symmetry is probably something we would say in a more geometric scenario, automorphisms more for abstract structures, but essentially it's the same thing, okay? Symmetry is the nicer term, so I like to use it here in this talk, but really it doesn't make that much of a difference, okay? So that's one thing. Now, let's look at another closely related notion. So again, here we have an octahedron, and automorphisms or symmetries are mappings from this object to itself that leave the object unchanged, the overall object. So if we reflect on this plane, say, well, it will be flipped, but overall it's still the same, okay? Here's an example, so that's a bit hard to see, but what I'm saying here is, okay, I just say what my symmetry does on the corners of the octahedron, and I flip these two, and I rotate the other four by 90 degrees. Okay, that would be one example of a symmetry or an automorphism. And the crucial thing is, we have mathematical properties of this object, and we would require our automorphism to preserve these properties. Okay, and in this case it would probably be the distances and the angles and just the geometric shape. Okay, we have a closely related notion, that's the notion of an isomorphism, which is now a mapping between two objects. Okay, we map one octahedron to another one, which is, well, it's obviously a bit different. It's turned a little bit, but essentially it's still the same. And again, we want to capture this mathematically, and the notion that captures this would be that of an isomorphism, which is a mapping from one to the other, preserving the mathematical properties. So I've indicated one such mapping here. There are actually many such mappings. For example, if I take such an isomorphism and compose it with any automorphism, I have another isomorphism. So this nice structure that we had for the automorphisms, for the symmetries, to some extent carries over to the isomorphisms. Again, this is something we will use. And now, let's move on from these general remarks to the questions I want to talk about today, and that would be, how can we efficiently compute symmetries or detect symmetries? That's really the core question I want to ask, and I'm going to ask it in a fairly general context, but not completely general. I want to look at discrete, at finite structures mainly, at symmetries of finite objects. That's probably my view as a computer scientist. Most of the things we talk about are just collections of bits and so on in the end. So finite objects are very natural for us. And with this restriction, the type of objects I'll look at are fairly general. Okay? So we come to this problem known as the graph isomorphism problem that Dan already mentioned in the introduction. And the objects, the structures we want to look at are graphs. Okay? I guess many of you have seen them. I will tell you what they are anyway. It seems that scientists, except for mathematicians and computer scientists, prefer the term networks, but it's really the same thing, and it's a very basic, discrete model that is used, well, in computer science, but also in many other disciplines. Okay, so I'm currently talking to people in chemical engineering who are very interested in machine learning methods on graphs because they use them in all kinds of situations. So it's really a very basic model, and you can put and translate many other models into graphs, so this makes this whole endeavor fairly general. Okay, so what is a graph? Well, formally it's a finite set whose elements we call vertices or sometimes nodes, and another set of elements called edges, and the edges are just pairs of vertices, unordered pairs. And the way we usually display such a graph is like this. So we have these black dots here. They are the vertices, the nodes. And then we have the lines connecting two dots, and that's the edges. That's basically, an edge is the pair of its endpoints. That's why I'm saying unordered pairs of vertices. Okay? So never mind this definition, just think of something like this when I say graph. Okay? There's also a directed version of graphs where the edges are actually arcs, have a direction, or are ordered pairs of vertices. For the purpose of this talk, the difference is really not important, so I'll just stick with undirected graphs. Most of what I'm saying is general enough that it easily carries over to directed ones as well. Okay? So now we want to talk about automorphisms and isomorphisms between graphs. And I said isomorphisms and automorphisms are mappings that preserve the mathematical properties. So what are the mathematical properties here? The one property we care about is whether two vertices are connected by an edge or they are not. Okay? So an isomorphism would be a mapping between the vertex sets. Okay? And that mapping should be a one-to-one mapping or an invertible mapping because I want my symmetries to be invertible. And it should preserve the edges. So I map edges of the first graph to edges of the second and non-edges to non-edges. Okay? So that's the notion, this general notion of isomorphism transferred to the structures I'm here interested in here, graphs. And an automorphism or a symmetry of a graph would be an isomorphism of the graph to itself. So it would be a mapping on my graph that doesn't change its structure. Okay? So here we have an example. That's my graph. Here's an automorphism of the graph, an isomorphism of the graph to itself. So what I do is I leave these two vertices fixed and I flip these two. Okay? Now compared to the octahedron, which I viewed as a geometric object where the distances and all that matters, here distances do not matter. It doesn't matter that the edge from here to here is longer than the one from here to here. I don't care. That's just an artifact of my drawing. What I care about is that there is an edge from here to here as well as from here to here. So that's fine, this mapping. Okay, another example, I have a second graph. Now I want to look at an isomorphism, and you can maybe see that the graphs are the same. So basically the mapping we want to do is we flip this out, and then we turn it, and then we more or less have the other graph, or a mapping would look like that. Okay, now of course this is something, now if we imagine we have 10 nodes, or usually in practical situation we have thousands. This is really a presentation where you can't do anything with these red arrows. So a nice way of representing such an automorphism would be just to number the vertices, and then your isomorphism would just match vertices with the same numbers. So to check that this is correct here, we would, for example, have to check that 1, okay, has 2 and 3 as neighbors here and here as well. Or 3 has 1, 2, 4 as neighbors, and that's also the case here. Okay, so this way we can do it, and let's look at another example now. Oh, one last thing I wanted to mention on this slide is that if there is an isomorphism between two graphs, we would call them isomorphic. Okay? So look at these 4 graphs. Now you can ask yourselves which of them are isomorphic, which are not. And it's not, of course, they look very different, but in fact they aren't. They are all the same. They are all isomorphic. But even for these small graphs, just 8 vertices, it's not so easy to see. For some of them, I guess you can see quickly. For some, maybe not so quickly. So let's again, let me show you how we can check. I've numbered them all in a consistent way, and now we can go through this. And, well, we don't really want to do this, so let's just do one spot check. The vertex 4 here has an edge to 3, 5, and 8. So let's look at 4 here. Now I hope I got this right. Yes, it has an edge to 8, to 3, and to 5. Okay, and you can check all the rest, or rather have a computer do this. Okay? Now, checking that this is correct is a tedious task, but very easy. You can easily program a computer to do it. If you just look at this, finding the right numberings, finding the isomorphisms is not so easy. Okay, and that's the problem we're interested in. Okay, so that's the computational problem, graph isomorphism, or GI. We're given 2 graphs, and we want to decide if they are isomorphic. Probably we also want to find an isomorphism if they are isomorphic. But if we can decide this, we can also find one. That's not really the issue, so let's stick with this very simple problem. So why is it difficult? Well, what would be the naive way of doing this? We would basically check all mappings, okay? It's just that there are really a lot of such mappings. So if we have graphs with n vertices, we have n factorial potential isomorphisms, and it's not an option to go through all of them, at least not for graphs of size, say, 100. I think there already we have more possibilities than there are atoms in the universe. Okay, so that's what makes this problem at least potentially difficult. On the other hand, something we noted on the previous slide, once someone gives us the mapping or the right numbering between the 2 graphs, to check this is tedious but just routine. That's an easy task, at least for a computer. Okay? And this puts this graph isomorphism problem into a class of problems that is well studied in computer science, because many problems one finds in practice are of this form. These are problems where it's difficult to find a solution, but once we have a solution, we can at least check that this solution is correct. Okay? And this class is called NP. It stands for non-deterministic polynomial time. I don't want to get into this, but this is really the realm in the complexity landscape we're living in here. Okay? One thing I wanted to note is that the graph isomorphism problem is equivalent to the problem of computing the automorphism group of a graph. So that I call GA. So there the problem is, given a graph, we want to compute all automorphisms. Now that's a bit weird, right? Because I just said this can be really a lot. So actually what we want to do here, we want to compute a compact representation of that group. And the way we would do this is we would compute a generating set for this group. So basically by multiplying these together, we would get all automorphisms. And we know we can always find a sufficiently small generating set. And with this agreement that we use that representation, it can be shown that the two problems are equivalent. And actually, when we attack, say, the isomorphism problem, we almost automatically also think about the automorphism problem and the other way around. So they are really essentially the same problem. Okay. So the question is, and that's this open problem that has been around for many years in computer science. The question is there an efficient algorithm solving this problem? Deciding whether two graphs are isomorphic, computing all automorphisms of one graph. Okay. Now, of course, what does efficient algorithm mean? Well, we don't worry too much about this. There's a standard mathematical formalization of this, which is polynomial time algorithm. So that means if we have an input of size n, say a graph with n vertices, we want our algorithm to run in a time or make a number of steps that is bound by some polynomial function in this input size n. And that's a reasonable enough approximation of efficient algorithm that it's widely adopted in theory. Okay, so now we can look a bit more at this complexity landscape. So we have this class P of all problems that can be solved by such a polynomial time algorithm. And we have the class NP of problems where we don't know whether we have such an algorithm, but at least once we find a solution, we can check efficiently that it's a correct solution. Okay, and then we have this little region up here, NPC, that stands for NP complete. These are, in a sense, hardest problems in this class NP. And what this means is if we can solve one problem here, we can solve all of the other ones efficiently. Okay? So, the interesting thing about graph isomorphism is that it's really one of the very few problems for which we neither know whether it's here or here. For most other problems we find, we can either show, and that's usually not even difficult, that it's NP complete, or we can show it's in polynomial time. For graph isomorphism, despite serious efforts for, well, 50 years, we don't know how to do this, okay? And at least for theoreticians, like I am one, that's what makes this problem so interesting. Okay, so let's see how this problem arose. Actually, it was first studied in chemistry. In the 1950s, people were building chemical information systems. And the idea was, well, we describe molecules by such graphs that you've probably all seen, and we put them in a database. And now we have this database of these molecular graphs, and we find a new molecule. And we want to know, is it already there in the database or not? Okay, then we have to match this to all the graphs in the database. And then we have to solve precisely our graph isomorphism problem. Okay, and the chemists were really the first to look at this, at least at this computational problem. So this is an early reference, a science paper from 1957, where they're thinking about this. Okay, computer scientists came a bit later. Actually, at that time there wasn't even computer science. But the first computer science papers I'm aware of are two papers from 1964. In the 1960s, people tried to find reasonable algorithms for this, but they didn't have the tools to to analyze, for example, the complexity of such problems, because the theory only evolved in the late 1960s, early 1970s, but then in the 1970s this came up. So in a very famous paper by Richard Karp, he showed that many natural problems, combinatorial optimization peoples that have been studied, all fall in this little red region of my pictures. They are all NP-complete. Well, he also looked at graph isomorphism, but that's one where he couldn't show this. So he mentioned this as one of the open problems in that paper. Also later in a very influential book by Gary and Johnson, it was one of the open problems, and it's, I think, the only one or one of two still remaining open, okay? Okay, people tried to do something about this, and towards the end of the 1970s, they got a bit frustrated with this problem. So they started to talk about the graph isomorphism disease, as you can see from this title of another very influential paper. Okay? And then in the early 1980s, something new happened. Finally, people brought in group theory. I mean, we have this problem, and we know its solution space exhibits this nice structure. It's a group, so we should use this. And Lazi Baba was the first to propose this in a paper that was just a technical report, never even published. But then people picked this up, and the real breakthrough was a paper by Eugene Lux in 1982. Actually, the conference version appeared a bit earlier, where he really used group theory. And the problem he solved is, he said, for graphs of bounded valence or bounded degree, that means every node has only a bounded number of edges going out. He showed that isomorphism can be tested in polynomial time. But what makes this paper so important is that he proposed a framework, a group theoretic framework, that is really the foundation of most subsequent work. And we'll come to that later. Okay? So this was a very important paper, and then there was, over the years, some progress, but it was also kind of slow. The problem was still open, and then only 4 years ago, Babai came up with an algorithm putting graph isomorphism, well, not quite in polynomial time, but almost in quasi-polynomial time. I'll tell you later what it means. For now, you can just see that the means of communication have changed in the 30 years between these papers. So that's a YouTube video of a lecture he gave. Well, they have not totally changed. I guess blackboards have been around in 1980 already. Okay, so this was a really important result that received a lot of attention, was called the most important result in theoretical computer science of the century. And I think that's true. It's an 80-page paper. It's not easy to read, but really had a wealth of new ideas. Fortunately, I won't be able to tell you too much about these ideas. That would be a different lecture, I guess. Okay, so what I also wanted to say at least a few words about is practical graph isomorphism. So can we... So I told you many reasons why I am, as a theoretician, I'm interested in it. But the problem has practical relevance, actually a lot. And the interesting thing is, it can be solved pretty well in practice. And Brendan McKay, around the same time as Lux came up with this group theoretic algorithm, Brendan was a master's student in Australia at the time, came up with a tool he called Naughty, and that worked pretty well. That's, you know, for many practical purposes, this just solved graph isomorphism. And, well, he continued to optimize it over the years. Other people also developed tools. Right now, Naughty is still state of the art. There's now a combination of Naughty with another cool a tool called traces, and that's really working well. And actually, what is difficult is to find graphs where this doesn't work. You can publish papers about this. That's what one of my students did, and it's really tricky. So for all practical purposes, graph isomorphism is solved unless you have really, really large graphs. Then these tools don't work. But that makes most problems difficult. So, and why are we interested in this problem anyway? There's basically two types of applications where we use, for example, these tools like Naughty. And one is probably what you would think of. That's the chemical information systems application. We want to match two graphs and see if they are the same. Something like this also comes up, for example, in face recognition, where often the features of a face are modeled by a graph, and then you just want to match two graphs to see if it's the same face. Or in many other computer vision, machine learning type problems. Another interesting application is malware detection. So you want to find a computer virus. So what you do is you match code fragments. And so I'm saying here static program analysis. So basically you look at the code rather than run the program to test. Okay, so these applications. Then there's a second group of applications which are very different, I think. And well, I call them symmetry breaking and symmetry reduction. So the idea there is if you have hard problems, you can often use hard algorithmic problems, you can often use symmetries to just shrink the search space. So if you detect symmetries in the problem, then you just know that certain combinations of values you don't even have to try because it's just symmetric to something you have tried earlier. And again, this has quite a few interesting applications. Now, if you look at these applications, very often we don't have to solve the exact isomorphism problem, but what we would rather need is something like approximate isomorphisms. This is just something to keep in mind, and that leads to my second topic, similarity, where I'll say a few words about in the end of my talk. Okay? But now let's stick with isomorphism for the time being, and I'll tell you a little bit about algorithms for the isomorphism problem. So, I'll start with an extremely simple algorithm that goes a long way. That's called color refinement, or sometimes naive vertex classification, or sometimes one-dimensional Weisweiler-Liemann algorithm. What it does, it computes a coloring of the vertices of the graph. And the idea of this coloring is to assign different colors to vertices that are different, that can't be mapped to one another by a symmetry. Okay, and the way we do this is as follows. Initially, all vertices get the same color. We know nothing. And then we do refinement steps. We refine our coloring. So I'm just using coloring as a fancy or a simpler term for partitions. So we have a partition of the nodes, and if we find a distinction between nodes, we put them in different classes of the partition. Okay, and the way we do this is we say two nodes get different colors. If there's some other color we have already defined, such that the two nodes have a different number of neighbors of that color, a different number of edges into that color. Okay, and we go on with this until no more refinement occurs. And let me just show you how this works. I have a nice demo of this. Okay, so here we see a graph. It's just some random graph with parameters that work well for the example, and you see initially all vertices have the same color, blue, okay? And now, what I was saying is, in the next round, vertices get different colors if they have a different number of blue neighbors. So a different number of neighbors. So this one should get a different color than this one. Okay, let's see what happens. So this indeed happens. So this here is now red, this is green. Okay, and now we look again. Let's look at these two yellow nodes. This one has two red neighbors. This only has one red neighbor. So they should get a different color in the next round. Okay, and they do. And we can look again at two nodes that still have the same color. Now it's already hard to distinguish the colors. Well, I guess you get the idea. And let's just move on and see what happens. So now, after 5 rounds, nothing happens anymore. And that's the final coloring we get. Okay? So that's how it works. That's something we can implement in a way that it runs extremely efficiently. So that really works well. It's just not clear what it actually does. So let's go back here and see if we can understand this a little bit. So first of all, what we're trying to do here is not find symmetries, but rather find non-symmetries. We want to be able to distinguish nodes that clearly cannot map to one another by an automorphism. Okay? And very often, well, we hope that we detect all non-symmetries, so that vertices get the same color if and only if they can be mapped to one another by a symmetry. That would mean they belong to the same orbit, as we say, of the automorphism group. So that's the hope. And actually, this works on almost all graphs. In the sense that if I take a random graph, with very high probability, this will work. Okay? And the random graph model here actually doesn't matter. However I do this, this will work for random graphs, because it's very unlikely that random graphs have symmetries at all, or any significant symmetries. Okay? So that's nice. On the other hand, there are very simple examples where it doesn't work. So look at this one. It's a graph on 7 nodes, and what would color refinement do on this graph? Well, nothing. Initially, all vertices have the same color, black. And now, in the first round, we look, oh, every node has 2 black neighbors. So nothing happens. They all stay in the same class. Okay, so they would all get the same color, but clearly there's no symmetry mapping this one to this one. Because this one is in a triangle and this is not. It's in a quadrangle. So clearly here our algorithm fails. Still, it's a very nice algorithm. It's so efficient. So we want to use it. So people in practice use it. And what they do is they build on this algorithm. So when it gets stuck, they just basically make a decision and then try out all possibilities. Basically, they individualize a vertex in one color class and then continue. And then do this as long as they have to, until they have a coloring where all nodes have different colors, and then from there it's easy to decide algorithms. So they build such a search tree like the one depicted here, and I don't want to go into any details. Then they use a lot of clever tricks to kind of keep this search tree small, and this is how all practical algorithms work. Okay? So much for that. So in theory, we also build on this, and one idea is to say, okay, so we color the vertices of the graph basically by locally trying to explore what asymmetries, what differences we can see. Well, instead we could also color edges. And then if you think about it, coloring edges, okay, we can do this. Then we can also color triangles. Or how about looking at non-edges? What difference does it make at pairs of vertices where there's no edge? Okay? And basically, if you want to do this in a systematic way, you just say, let me color k tuples for some k. Okay? I can color, say, triples of vertices or just pairs or whatever. Okay? And my running time will depend on this k, this dimension. It will take longer to color triples just because there are more triples. But I can do this, and then I can, again, I can look at, say, all triples of vertices, gather the local information I can find around them, and then propagate this and do this iterative process. In the end, I end up with a coloring that gives me a lot of information on the structure of my graph. And this idea, well, for the case of just coloring pairs of vertices is due to Weisfeiler and Lehmann. That's why this algorithm is called Weisfeiler-Lehmann algorithm back in 1968. And the generalization is due to Babai from the early 1980s. Okay, so here you see a coloring. The underlying graph is just a cycle, and that's the coloring of the pairs you would get. Okay, again, I don't want to go into any details. So that's a very interesting algorithm. Well, it generalizes the color refinement, obviously. That's the one-dimensional version. What is nice about it is it also subsumes many other combinatorial algorithms. So whenever I speak about graph isomorphism after the talk, people come to me with ideas of what they can do. And usually, I mean, essentially always, three-dimensional Weisfeiler-Lehmann subsumes this, is more powerful than this. It really does a lot. Interestingly, it also subsumes other approaches based on mathematical programming, linear programming, semi-definite programming, or other algebraic techniques like Gröbner basis techniques. All this is essentially either equivalent or weaker than this algorithm. Okay? But then, unfortunately, there are also graphs where it completely fails. It's quite intricate to construct such graphs. Well, that's something Führer-Immermann did in a very important paper from 1992. So, where does it leave us? We have basically, using Weisfeiler-Lehmann, we have systematically explored this combinatorial idea of propagating local information. So now let's really move on and do the proper thing and look at the automorphism groups. Okay? So we know the solution space to our problem has a nice structure, a group structure. So we should do something about this. But how can we? And this is what Lux did in a very nice way. He introduced a framework, a divide and conquer strategy for solving, well, the automorphism problem now, but this is equivalent to the isomorphism problem, so it's really the same. And very roughly how this works is, okay, we want to compute the automorphism group. We start with some group that we can somehow find easily. Now, I know I'm very vague here, and that we know is a supergroup of the automorphism group. For example, you can think of just taking all permutations of the vertex set of a graph in that group. But that may not be the best starting point. And then we compute a sequence of smaller and smaller subgroups, better and better approximations of the automorphism group, until we finally have the right one. And now the way we do this is basically by exploiting the structure of such groups, permutation groups we have here. We look at orbits, we look at blocks and so on, and we get smaller and smaller groups, also maybe smaller sets on which we operate. And then we get stuck at some point, and that's when we hit primitive permutation groups. Now, I don't want to explain what they are, but here they come up as a bottleneck. But then we can do something. We know a lot about primitive permutation groups. Group theory tells us really a lot about them. There's this huge project of the classification of finite simple groups that sheds a lot of light on them. And then the hope is to be able to exploit this group theory and make progress there. That's how these algorithms work. And let me just show you a few results and then leave you with that. So n is always the number of vertices, and this algorithm Lux came up with in 1982, says isomorphism of graphs of maximum degree d, so degree again is the number of neighbors, can be decided in time n to the d roughly. Okay? This has been improved a little bit a year later to n to the d over log d, but not since then. And then suddenly in 2015, Babai came up with this algorithm based on the same paradigm, but using much more sophisticated techniques to deal with this case of primitive groups. And what he achieved is quasi-polynomial time. That means it's time n to some polynomial in the logarithm of n. Okay? So that's kind of close to polynomial because we think of logarithms as being fairly small. Okay? So this is the best we can do for the general problem. Now subsequently, what we could do is then, in a way, put the two things together and decide isomorphism of graphs of maximum degree d in time n to some polynomial of log d. So that's the first improvement of this Lux thing in a long time. But for graphs where the degree is not so big, it's also an improvement of Babai's algorithm. Okay, and basically what these algorithms do, they use increasingly deeper results from group theory, and they also use some combinatorial tricks. In particular, Babai uses some very intricate combinatorial arguments. So that's basically the state of the art on the isomorphism problem. And the last few minutes I want to use to talk about similarity. Okay? Okay. So the starting point would be that symmetry is rarely perfect. And let's look at another Sumerian picture. And this one is quite interesting. Okay. Well, there is on the surface, again, a mirror symmetry between the two sides. Kind of obvious. It's not perfect in one way. Well, the antlers of the deer are not exactly the same way, but ignore this for a minute. There's another very interesting thing here. If you look at the legs of the deer, they are like the hands of the figures in this second thing. You would have to rotate. But now you look at this lion-headed eagle here, that you clearly cannot rotate. So this is a weird picture, and I'm wondering if they were aware of this and why they did it this way. Anyway, my point is here, most of the time we don't have exact symmetry, exact isomorphism, but only approximations of it. And we should think about this. And if we want to think about computation, we should also study the computational complexity of these problems. Okay? And if you look at the literature, well, there is a lot in machine learning. There's very little in theory, interestingly enough. And maybe one reason even to start with is, it's not, if we go back to graphs, it's not even clear what similarity of graphs is supposed to mean. So let's look at these very small graphs, okay? Let's look at these two first. Well, they are similar in a way. Both cycles, it's just that one has one more vertex. So we would probably call them similar. Okay? Now look at these two. They are also similar. Again, both cycles. Now we kept the number of vertices, and the one vertex we took out of the cycle, we put as an isolated vertex. Okay, so still maybe similar enough. Now we look at these two. They don't look similar at all. However, it turns out that they are co-spectral. If we look at their adjacency matrix, it has the same, the matrices, they have the same eigenvalues. That's a weird mathematical way of looking at similarity of graphs, I admit. But actually in practice, and again in machine learning, these things are used. This is a quite useful way of seeing it. Okay, so in this sense, these two are also similar. Or now let's look at these. Also, not really that similar, except that they are similar because the color refinement algorithm cannot distinguish the two. Again, that's a useful criterion. So, where does it leave us? It's completely unclear how to measure similarity of graphs, or the related problem of vertices within one graph. Okay? So, that's the first problem. The second problem is, similarity is not transitive. While all these pairs may be similar, maybe this and this one are not similar at all. So, symmetries compose nicely, similarity not. It's not a good notion, so we lose all the nice structure. And it was precisely that nice structure that gave us a handle on algorithms. So basically, we're completely lost here. And actually, this can be observed. Both in theory, we can show that similarity with respect to most measures we can come up with is a hard algorithmic problem. For example, it would be NP complete. And also in practice, it's an extremely hard problem. Even among the theoretically hard problems, this is one that is particularly hard, and that people, say in combinatorial optimization, can only solve on small instances. And that may explain why there's so little research on it. Still, it's an important problem. And in particular, people in machine learning, computer vision have studied it for a long time, completely unnoticed by theoreticians, but they have papers with thousands of citations on precisely this problem, which they call graph matching. Okay? And for example, if you think of faces, all kinds of objects, they are never exactly the same, so you have to deal with this similarity, and if you model things by graphs, you have to deal with similarity of graphs. Okay, and then if you want to learn properties of these graphs, well, basically the idea of machine learning would be that similar things get similar classifications. Okay, so it's very important there. And something that is done there, and which is also very interesting from a theoretical perspective, is to look at vector embeddings of graphs. Now, that's a big step from similarity. So what we do is we take our graphs and map them in some way into vector spaces. Okay, so points in some vector space. Maybe an infinite dimensional space. We want a distance measure on it. So formally we want it to be a Hilbert space. But sometimes it can be useful even to think of infinite spaces, sometimes finite. And then the idea would be that the distance between 2 points here should somehow correspond to similarity between the graphs. Okay, so the embedding should carry a semantic meaning. Okay, and now there's various ways of achieving this. I don't want to get into these too much, but that's a very good way to think about this problem. And actually, it tells us a lot about the graphs, because now we can essentially do calculus on graphs. We map them to some continuous space, and then we can talk about limits and all these things. So that's actually a very nice topic. Okay, so as I said, they have been extensively studied in machine learning, but also a little bit in mathematics. Now, in machine learning, one classical method are graph kernels. They are basically deterministic vector embeddings into very high-dimensional spaces. And one well-known graph kernel that works extremely well in practice is derived from our color refinement algorithm. It's called the Weisfeiler-Liemann graph kernel. So basically, the information we put into these vector embeddings is the information that the color refinement algorithm gives us. And that basically is We just, in our vector, we put how many vertices are there in each color class. That's essentially what it does. Okay? Now, of course, these days, kernel methods are completely out of fashion in machine learning, and everybody does deep learning. So the method of choice there is graph neural networks. You can also interpret them as computing vector embeddings, where now basically they try to learn these vectors. So we looked at what they can do, and quite remarkably, what we could prove is that they extract exactly the same information from a graph, again, as the color refinement algorithm. And I want to leave you with this. Thank you.